Hi and welcome back. So in this video we're going to work on another optimization problem, and it's going to be maybe just a little bit more abstract than what we've been doing in the past few videos. And the problem that we're given is this. Let's say that S is going to be the set of all the rectangles that we can possibly have that have an area of 100. So S is the set of all rectangles where the area is equal to 100. So you can probably take a guess how many are there a finite number of rectangles with area where the area is going to be 100? And no, there are an infinite number of different rectangles. So there are infinity different rectangles that we could draw. We could draw, you know, kind of normal looking rectangles like this, and we could say, I don't know, that maybe this would be, that maybe this side could be 2, and then this side could be 50, and you multiply 2 by 50, and that gives you, so our area would be this side times this side, and 2 times 50 would be equal to 100. We could have another rectangle where we had, I don't know, say this side was 4, so it's going to be twice that length, and then this side, well, how long would this side be if this if our height was 4? Well, it would be half the length of 50, right? So it would be about to there. We could say 4 by 25. So again, our area is 4 times 25, and that would also equal 100. So these are both rectangles that are in our sum set S. That would be all the rectangles containing areas equal to 100. And what we are supposed to find, we are trying to find the area, or we are trying to find the rectangle with the smallest perimeter. So find rectangle with smallest perimeter. And hopefully you can see, in addition to, so I've drawn like 2 different examples of rectangles that we could possibly have in this set that is all rectangles that have area of equal to 100. And imagine we had a rectangle where its height was really, really, really small. Say it was, you know, just, I don't know, say it was 0.0001. So this is 1/10, 100,000, so this is going to be 1/10,000th of a unit tall. And so that means that it is going to have to be really, really, really wide. So it is going to have, and it would definitely keep on going if we were drawing this to scale, if our height was going to be so small. And you can imagine that our height would be the reciprocal of this. That it would be, so if this is 1/10,000th, so if you multiplied this by 1, 2, 3, 4. So if you multiplied this by 10,000, you would get 1. So you would have to multiply this by 10,000 times 100 to get 100. So that's what the width is going to be really long. It's going to be 10,000 times 100. And what would that be? That would just be 10,000 with, so that would be 10,000. That would be 1 million, right? So that would equal 1 million units. And then what would the entire perimeter be? Well, it would be this 1 million times 2, right? Because we've got two lengths of 1 million. So it would be 2 million plus 2 lengths of our height. So the entire perimeter on this would be 2,000,000.0002. That would be our perimeter for this. And similarly, think about this. What would it look like if we kind of had the inverse of this rectangle, where instead of saying we had our height was really, really small, what if our width was really, really small? And instead we made this rectangle that its width was only going to be 0.001. Well, again, we would have this really skinny but really tall rectangle, and it should keep on going, but you can see that it would really just kind of look like a line, and this width would be 0.0001. And again, our height in this case, our height would be 1 million. And again, our perimeter would be this figure. Our perimeter would still be equal to 2,000,000.0002. And hopefully you can see that we've found a couple of rectangles that are in between. So we found a couple of rectangles that are, this is kind of one extreme where our height is approaching 0. This is another extreme where our width is approaching 0. And in both of these, our perimeter was really, really big. And now you can probably imagine we can find a few rectangles that are in between these two. So some happy medium somewhere that our perimeter might be a little bit smaller, but our area can still be 100. Let's just think of one. So let's say we had a rectangle. Let's actually let's say that this length, let's say we have a height of 5. And then what is our width going to be? Because we have to multiply 5 times whatever our width is going to have to be 100. So we can say that this is going to be 20, right? Because 5 times 20 is going to give us 100. And what's the perimeter of this going to be? Well, the perimeter, it's going to be 20 times 2, because we have two sides of length 20, so it's going to be 40 plus two sides of length 5. So it's going to be 40 plus 10, or 50. And that's going to be between these two really big perimeters, right? So it makes sense that somewhere between these two rectangles, these two extreme rectangles that have these extremely big perimeters, because we still have to fit 100 square units of area into this really, really skinny space in both of these situations. It makes sense that somewhere in between these two, where we have a really skinny height but a really big width, and here we've got a really skinny width but a really, really large height, it makes sense that somewhere in between we're going to find that our perimeter is minimized, where we still have an area, where we still have a rectangle of area 100, but a perimeter that is going to be a minimum, where we will find a rectangle with the least perimeter. So let's go ahead and write down what we know. And let's do this with sort of an arbitrary rectangle. Let's scroll down a little bit more. Let's say this will be our arbitrary rectangle. And actually, I am going to make these sides a different color. There we go. And I'm going to label this side X. So we've got X, and then the top and bottom are both going to be Y. And let's say, so what is our area going to be? Well, it's going to be the base times the height, right? So it's going to be Y times X. And we already know what the area is going to be, right? So we know what Y times X has to be. It has to be equal to 100. So this is the condition, that this is the relationship that we know about Y and X. So for any X that you pick, and I could explicitly, actually, you know what, let's go ahead and just explicitly define Y in terms of X, where we could say, we'll divide both sides by X, and we can say that Y is going to be equal to 100 over X. So now you can see that for whatever height For whatever height of a rectangle I choose, where I choose, like, okay, say I choose 5. Well, I know that my y value, my width of this rectangle, my width is going to have to be 100 divided by whatever I chose here. So y is going to be equal to 100 over x. And now let's also figure out what is our perimeter going to be for this entire figure. Well, it's going to be, we've got 2 of these x segments, and we've also got 2 of these y segments. So let's call this P. P is going to be equal to 2y, switch colors, plus 2x. So we've got each of these segments, and now we've also got y explicitly explicitly defined in terms of x. So let's just go ahead and plug that into this equation. So now, let me write that in, and I'm just going to write this in one color. So we've got P, and we can even call this P of x, is going to be 2 times 100 over x plus 2x. So we now know with this equation that we've got, for any x that I choose, for any x that that I choose for any rectangle that I'm making that has area of 100, I can now tell you for any x, and I guess it would be any x between 0 and well, actually, yeah, it would be between 0 and really infinity, I guess. I can tell you exactly what the perimeter would be for any x that you want to choose for your rectangle. So this is what we have figured out. So this is essentially the function that we have to minimize. And so we've made an important, I guess, first few steps in just getting this equation. And I'm out of time now, so I will continue with this in the next video. Thanks for watching.